Hello, physics fans. I am going to do TP 11 or 10-93. It is a Newton's second law problem, and I thought it would be good to touch on some of the things that are important for Newton's second law. So let's start. Let's look at the diagram. It is a block that is sliding down, and it has attached to a cord and a pulley. Now, let's do something here just for the heck of it, which I think you will find it beneficial. We don't really talk a lot about applied forces, so I'm going to add an applied force to this problem, which will be a little bit different from the actual problem itself. And this applied force will be denoted as F. It is completely parallel to the surface. So that's okay, just to identify that it is parallel horizontal to the surface here. Now, let us continue. It is sliding down, and this time around it is also being pulled down because of the force being applied. And has an angle of 45 and has a pulley with a mass of 1 kilogram and a radius of 0.5 meters. Whenever you see a radius and a mass, it means that the pulley has inertia, and because it has inertia, we also are considering torque. So let's start putting in the equations. We have the sum of all external forces is equal to mass times acceleration of the system. Okay, so of this system. But we also, since we have torque, we are also considering the sum of all external torques, thanks to that pulley, is equal to moment of inertia times angular velocity. So we identified those, and given that it is a moment of inertia and we have a radius and we have torque, it is also important to write down that torque equals the cross product of the distance from the axis of rotation to the point of application. Okay, so we'll talk a little bit more about this equation once we get there. It says that the pulley can be approximated as a disk. Okay, so looking at the PRC and looking for the moment of inertia of a PRC, this is important. The reason why they describe this to us is so we can find the moment of inertia. And the moment of inertia is 1/2 mass times r squared. So we write it down. It's moment of inertia, 1/2 mass times r squared. Okay, so we have identified most, if not all, of the physics that are important. And actually, one last thing, since we're dealing with a rotational object, and it is a rotation that we're gonna assume is uniform, the acceleration is not uniform, but it is rotating. It is definitely rotating, so it would be acceleration is equal to the radius times the angular acceleration. And the reason why this is important is because we are dealing with a tangential force that is acting on the pulley. And I'll go a little bit more in depth into it, but this tangential force is also, if you put in a tangential force that is touching the pulley, if you go 90 degrees into the pulley perpendicular and go straight down, this perpendicular line is going to hit the center of the circle. So we are experiencing a tangential force. And it's also important to note because as it's rotating, as a circle or the pulley is rotating, it is experiencing an angular acceleration. So this angular acceleration can be experienced in any place along the circle. It can be experienced here. Angular acceleration is the same here as in here as it is in here. Their angular acceleration is equal in every part of the circle. But when we go and talk about the tangential acceleration is a little bit different. So while the acceleration, the angular acceleration is the same all around the circle, if I chose this tangential acceleration here, and let's put it as tangential acceleration as 1, and then this tangential acceleration here, tangential acceleration 2, these two accelerations are different because they have different radius. So given our equation, and I already have it here, given our equation here, notice that as my radius increases, so will my tangential acceleration. In this case, acceleration 1 is smaller than acceleration 2 because of the radius. The radius is smaller. That's why we have to account for the link equation, which is A equals radius times the angular acceleration. Okay, so we talked about that. Now let's go to the draw. And I am doing this in the sense of the WPR, like things to tackle first. First thing is write down the physics equation, and second thing is go straight to the draw. For everything else, you can literally underline it. So it says, what is the acceleration? Just underline it. That is your task. Find the acceleration. Make sure that even if it comes down to it and you don't know how to solve the problem, at least tell us that you're trying to solve for acceleration. Okay, so the first thing is identifying the systems. So we have two systems here. We have the block and the pulley. They're two separate systems acting on an overarching system. Okay? So we have two blocks or two systems, and we're going to deal with the first block first. Let's go through identifying all the forces in that first block. We have the 1F equation. In the 1F equation, we identify weight, we identify applied force, we identify normal force, tension, and frictional force. So when it comes to normal force or weight, the weight is going straight down into the center of the earth, from the center of the object. Okay, so scratch that. We have identified the weight. Fantastic. Now, let's identify the applied force. Okay, so applied force, there is an applied force because we talked about it, and this is force. So applied force is the force F, and we cancel that. By the way, I am only solving this algebraically. So like I'm doing the calculations itself. This is only to show you how to do it algebraically. Then normal force, it is always perpendicular to the surface in which it's standing on. So this surface right here is at a 45-degree angle. Because it is at a 45-degree angle, my normal force, since it's perpendicular to the surface, is coming out of the page like this. Or not coming out of the page, but going upwards like this. Then we have the tension. Tension is always going away from the object in question. And we identify tension here. And finally, since this also has a coefficient of kinetic friction, it's telling us that it has friction involved. So it's sliding down and it's being pulled down. So friction always acts opposite of the direction of motion. Finally, for this system, we forgot one underlying thing is identifying the coordinate axis. And the coordinate axis is, the other way around. X and Y. X being in the direction of motion since it's going down, and then Y being positive and perpendicular to the surface where the block is laying on. So we're done with system 1. Now let's go to system 2. System 2 is the actual pulley. So the pulley itself is a circle, and this, even though it doesn't really show here, it is tangential to the pulley. This is experiencing a tension in that pulley. But again, as I said again, tension is always going away from the surface, from the object, from the object. And since it's going away from the object, that's why I am pointing it towards the block, because we're studying right now the pulley. That doesn't mean that even though tension is the only force that we care about, because whenever we see a pulley, we solve it in terms of torque, not in terms of force. But it does still have a weight. So we still have weight that is acting on the pulley, and then there's still normal force that is going away, acting away from the pulley to make sure that it is still experiencing a contact force. But the key here is definitely the normal force. I mean, not the normal force, sorry. The tension. Okay, so the tension. One thing, too, is the coordinate axis. Since we're following the direction of motion of the block, make sure that you have identified that it is going counterclockwise as positive direction because you're following the direction of motion. Okay. So now we have both systems. We have identified system 2, and system 1. And we can rewrite this, or we can start plugging in or identifying all the forces for system 1. And let's do a system 1 right here. So system 1, we have to identify all the forces in the x and in the y direction. So one thing, going back to the block, is that the weight is acting on both the x and the y direction. If you put in the coordinate axis actually in the block, you'll see what I'm talking about. So this is negative y because positive y is upwards, and this, where I'm doing this, the little segments of lines, is the x. Okay? If we're giving a critical angle, and that critical angle is 45 degrees for the inclined plane, it will be the same angle found between the magnitude of weight, mg, and the coordinate axis of y. So this angle right here is going to be equal to 45 degrees. Now, because it is at an angle, it is acting both on the y and on the x-axis. The weight is acting on the y and the x-axis. The magnitude of the weight acts like the hypotenuse of a triangle. So we have, let me erase this, hypotenuse, which is the largest part of a triangle. And the angle right here, this angle right here tells us something really important. If we have the coordinate axis, or the coordinate of y here, and then the hypotenuse here, this vector right here, what I'm circling at, is going to be the adjacent, because the angle is located in between the weight and the coordinate axis of y. If this is adjacent, this means that this is opposite. Okay? And because we can rewrite it like this, where adjacent is equal to hypotenuse times cosine theta, and opposite is equal to hypotenuse times sine of theta. So opposite in this scenario, if I wanted the weight in the x direction, I would pick hypotenuse sine theta. So going back to the actual system, we have to identify all the directions of the forces. So let's start off by writing off the sum of all external forces in the x direction is equal to mass times acceleration. So mass times acceleration, and now we do know that there is movement going on in the x direction because there is motion going on there. Now let's put in, identify the first force, which is the applied force here, is positive in the positive x direction. Then we have minus the tension because it's going away from the direction of motion. And we also have friction, which is acting opposite of motion. So we identify that. And finally, we have weight, which weight is right here. Mass times gravity. And since it's acting in both the x and the y, we identify it as positive because it's also in the positive x direction. Positive x direction. We write mass times gravity times sine of theta equals mass times acceleration. Good, but we also are missing one thing, is the kinetic friction. Kinetic friction is written as coefficient of kinetic friction times the normal force. So we need the normal force. But the only way that to get the normal force is by solving it through the y direction. And it goes as the sum of all forces for this system in the y direction is mass times acceleration in the y direction. Mass times acceleration in the x direction, mass times acceleration in the y direction. Because it is not moving in the actual y direction, but it is moving in the x direction, but not moving in the y direction. Moving here, x direction. But there's no motion going on around here because we're following our coordinate system. Then we write down that mass times acceleration is actually 0. When identifying the forces in the x and the y direction, we write down normal force, because normal force is completely parallel to the y direction, minus mg cosine theta, because look at this now. Now we're looking for the adjacent, and the adjacent is hypotenuse times cosine theta, because remember, it is cosine and sine is not dictated by x and y. It is dictated by where the angle is located at the moment of analysis. So in the moment of analysis right here, when we have theta here, since it's between this y axis and the weight, the vector of weight, then we have to solve for adjacent. And adjacent is hypotenuse cosine theta for the actual, for the y direction. That equals to 0. Now we have normal force equals mass times gravity cosine theta. This is good because now we can solve for the friction, or at the very least, yes, we can actually solve for the friction, and we have friction equals kinetic friction, coefficient of kinetic friction times mass times gravity cosine theta. Notice that I just brought simply plugged in normal force into the equation, and now I have that. So now I have completed my system. I have identified all the things that I could for system 1. And I will write down tension. Actually, I'm going to solve for tension. And the reason why I'm going to solve for tension is because I want to make sure that, and let's be real, when it comes to the pulley and the block, the thing that connects both of them is the tension. So eventually you're going to have to plug in tension in one of the equations of the pulley, because tension is connected to the pulley system. Okay? So I'm going to rewrite tension is equal to force minus the kinetic friction, which is equal to coefficient of kinetic friction times cosine theta, plus mass times gravity, sine theta, minus mass times acceleration in the x direction. So we have the equation for tension. Now we have to do the relationship with system 2, which is the pulley. So system 2 is the pulley, and immediately after, right off the bat, since it's a pulley, you go the sum of all external torques is equal to moment of inertia times angular acceleration. Right off the bat. Identifying this, let me just get close by. Let me put this. Since we're solving for the torque, remember, torque is the analysis, the rotational force of an object when you're applying a force, and this force is tension in this case, and you're analyzing it from a distance to the axis of rotation. And this is the distance to the axis of rotation. This is where the R cross F comes from to analyze torque. The torque itself needs to be perpendicular. It has to have a perpendicular relationship. So the vector of the force has to be perpendicular to the vector of the radius in order for it to work. In this scenario, we already have it set up this way as being perpendicular. If it had an angle, let's say like this, if it was at an angle or something to this effect, and it not tangential or anything to that effect, then you would have to consider the angle here, and you would go RF sine of theta to analyze the torque. But in this problem, since it's tangential, when you add tangential, let me explain again. Tangential is when like it's touching the outer edge of a circle or like a curve. And if you put a perpendicular line from that vector right here, you can go straight down to the middle of that circle. And that is why we have a completely perpendicular line. And when we reanalyze it, it's RF sine theta. This is 90, sine of 90, and sine of 90 is 1. So RF. Okay? So we have that. We can erase this. Knowing this, the only torque acting on this system is the tension. The reason is because even though we have weight is acting straight down the middle of the circle. And remember, we need a radius, a distance, to have any type of torque. If we follow our equation where it says R cross F, we have no radius left on this, no distance from the axis of rotation. It is literally a force acting right down the middle of that circle. So this R distance would be 0. And thus torque would be 0 for the weight. But we have torque because of the tension that's acting tangential to the circle. So we write down T, tension, R, sine of 90, is equal to, and this is moment of inertia of the disk. We can go and check out that the moment of inertia of the disk is 1/2 mass r squared found in your PRC. And then talking again from the link equation, we have A over R. Translational acceleration over R. So now we're almost done because we have tension already. We have solved for tension already. And the tension here, we can, actually I'm going to just copy paste it. Copy, paste it. There you go. So this is tension, parenthesis, R, and sine of 90 is 1, is equal to 1/2 mass R squared over A R, times AR. So the radius can cancel out. Let me address this like this, R squared. The radius can cancel out because we have radius here. So this goes to 1. But then we have another radius right here. We bring it to the other side, completely cancels out. So all the R's are canceled out. And the only thing that you have to solve for is for the acceleration. So the acceleration should be some unit. And in this case, looking at the problem, the lowest significant figure is 1. So it would be 1 significant figure, mass over s squared, over s second squared. Make sure that you identify that it's 1 unit. And that you have identified, or not 1 unit, 1 significant significant figure, and you identify the unit correctly. Okay, I think that settles it for this problem for Newton's second law. I'll hit you up with another Newton's second law problem as I see fit, but hopefully this problem will help you out. All right, thank you, and I'll see you for I'll make another video on electric fields and magnetism.